Perfect. So, yes, guys, until now we have seen the outline of the delta sigma modulator, and we have seen a sort of loop or a feedback loop where we have a loop filter followed by the quantizer, and we said that quantizer is a nonlinear block. So, we also arrived with a transfer function. So basically the V, which is output of the quantizer of a delta sigma modulator, is basically signal transfer function times U and noise transfer function times E. And this E is basically a noise or the white noise, which is basically error due to this nonlinear block. So we also said that in our signal band, the signal transfer function is approximately 1. So we were at this relation where we had V equals to U plus NTF times E. So basically signal at the input of the quantizer, which is Y, was given by U plus NTF times E, which is basically the output V minus the error, which is E. And this is something we considered that the quantizer uh, was to be additive noise source. And by assuming that, we said that yes, with the output is basically Y plus some additive noise source E. And from that assumption, we said that Y equals to U plus NTF minus 1 times E. So, however, a practical quantizer, along with having very bad nonlinearity, also has the saturation. So, it has its saturation limits. And within this voltage, our quantizer is working as a, I mean, in a proper way, or else out of this level our output of our quantizer is being blown up basically. So then, due to the non-linearity, the rigorous analysis or mathematical analysis of this loop is anyway not going to help us, and it will lead us to very complex mathematics, leading us to no intuition or no output anyway. So we approximate the best cut approximation of the quantizer, which is linear, which behaves linearly, and we apply the linear solutions to the system. So even though it's non-linear, so but we apply the uh, best cut linear approximation to it. So most importantly, we need to develop the intuition about the stability of modulator and changing the parameters, for example, the number of levels or the resolution of the quantizer and what it does to the stability of loop. So these things we should develop our intuitions in. So basically, we try to make the best cut linear approximation of the non-linear quantizer by saying that yes, our V, which is the output, is, if we consider, like for an example, we consider U to be DC, then we can say that the output has two parameters. One is coming from DC, which is YDC, and one is due to the noise, which is floating all over the loop. So we said that YDC times K1 plus N1 times K2. This is the exact linear system, but as it's non-linear, it is about, I mean, it's the best cut approximation. It's not perfectly linear. So then we also are left with the error. And we make sure that K1 and K2 are chosen in such a way that the mean square error will be as small as possible. So this error, basically this mean square error. So basically V minus YDC K1 minus N1 K2, and this mean square is as small as possible. So basically the error is as small as possible. So um, we can see the plot. So this is, I mean, if this is the DC, which we say, let's take 3.14. So then the YN is presented in blue. So basically that's the noise, I mean, riding over the input, which is DC. So this straight line is DC and the noise is riding over the DC to the input to the quantizer. And the quantized signal is given in red. And obviously the error, I mean, the difference between the quantized signal and the input is basically, uh, it's no surprise, but it will come out to be delta square by 12, and it is bounded by minus delta by 2 to delta by 2. So this is the error. So, and it's no surprise because error will somehow come because it's not perfectly linear, but it's the best cut approximation of a linear system. So then um, we said that going to higher order loop filter, so basically going to higher order L of Z, we got better SQ and R. So basically when we shifted to higher order NTF also, we got better SQ and R. I mean, the noise was shaped and the noise in the signal band was reduced significantly. So we would like to make L of Z to have as high gain at DC as possible. So given an NTF, so if we are provided with the NTF, we can always find L of Z as NTF is equals to 1 upon 1 plus L of Z. So as we discussed earlier, the system can be broken into two parts, and instead of having a quantizer now, which is non-linear obviously, now we can have two different systems. So as we saw in previous video over here, so we can have two different systems and we can have like one representing for the input and one representing for the N1 part, which is due to E, which is floating throughout the loop. So we have part 1, which is only dealing with YDC, which has gain K1, and other one, which is dealing with the error part with the gain K2. So let's focus on this one as of now. So basically what we do, so we have a quiescent input and we can represent a system. So we can represent a system by a quiescent input, and then we can represent its incremental loop. So we have the gain K2 and I mean the input is basically then grounded. So this is the noise part, dealing with the noise part. So instead of having a quantizer, we have a gain K2 plus some error E and the feedback. So the true transfer function or the poles are given by 1 plus L of Z times K2 equals to 0. So clearly K2 influences the location of the poles and basically therefore influence the stability of the loop, because the stability of the loop is totally dependent on location of the poles. So let's take a NTF of higher order. So basically where the main motivation of going to higher order is for better and better performance, right? So let's go to higher order. Let's take order 3. So let's take the NTF of 1 minus z inverse to the power 3. So then L of Z comes out to be 1 upon NTF minus 1. We can find poles using this equation, as we have L of Z from this NTF. And we can find the poles using this equation for K2 going from 1 to 0. So what do I mean by this? So basically we have a best cut approximation, right? So in the if it was perfectly linear, then our K1 and K2 would have been 1 and 1. But we have some error. So our K2 will be, the if it was perfectly linear, it would have been 1. And due to some error, it will be lesser than 1, maybe, and it will go from 1 to 0. So K2 equals to 1 corresponds to the modulator being in range of uniform staircase region of quantizer, and as the input signal gets closer and closer to the saturation limit, K2 will fall. So if we plot the locus of the poles of the system of K2 varying from 1 to 0, then we can see that basically for K equals to, K2 equals to 1, our transfer function is basically 1 minus z inverse cube. It comes out to be this transfer function. And over here, all our three poles, P1, P2, and P3, are at 0. So they are at 0, comma 0. So this is the position for the case K or K2 basically equals to 1. And when it falls from 1 towards 0, these poles starts moving in these directions. And at some point, the location of the pole breaks the unit circle. So for some critical value of K2, the poles cross the unit circle, and beyond that value of K2, system is unstable. So if we plot the magnitude of largest pole as a function of K2, then when K2 is equals to 1, obviously magnitude of pole is 0, and as K2 keeps falling, the magnitude of P keeps on increasing. And at some certain point, when magnitude of P becomes 1, or more than 1, and after that point, system becomes unstable. So it is somewhat about 0.5. So around 0.5 or something. So if K2 falls beyond 0.5, it is lesser than 0.5, then the magnitude of pole is beyond the critical point. So the system is unstable. So once the quantizer gain is falling below 0.5, the modulator basically becomes unstable. In other words, the input to the quantizer will blow up. So then the locus, this is for the third order. So the locus of poles for second order delta sigma loop is basically, given by, for example, the NTF is 1 minus z inverse to the power 2, 1 minus z inverse square. Then the L of z is basically 1 upon NTF minus 1. So from this L of z, we can find the poles for K2 going from 1 to 0. So for K2 equals to exactly 1, poles are located at 0 based on this equation. So at 0, when the poles are at 0, this is the case for K2 equals to 1. And as K2 starts falling towards 0, from 1 to 0, the poles starts moving in these directions. But in second order delta sigma case, as K2 keeps falling, the poles move, but they are always within the unit circle. And this analogy is somewhat similar to the analogy in continuous or analog circuits, where we have bichords. So second order function where the poles always lie in the negative half plane. So this analogy is somewhat similar to that. So in such kind of systems, so basically this is for second order systems. So now, generally talking, in such kind of systems, one must expect signal level dependent stability, meaning After a certain level, if the input to quantizer increases, the entire noise shaping property of the loop will be lost, as noise will become very large at the input of the quantizer, and the quantizer has its own saturation boundaries. So in other words, this property of making in-band noise very small can be achieved only by staying in the unsaturated region of the quantizer. So basically, this is the unsaturated region, or the input to the quantizer must lie within this range. And also, we need to keep in mind that the input to the quantizer, which is Y, and the input signal, which is to be digitized, which is U, are different. And clearly, you cannot occupy the full range of the quantizer because, it must be smaller by some amount in order to leave some room which can be accommodated for the shaped quantization noise, because the noise in the band, or the in signal band, even though if it's reduced, but it's not cut off, it's pushed to pi, higher frequencies. So over a range of pi, the noise will be large, or the variance of the noise will be large, which will be seen by the input of the quantizer. So in order to leave some room for shaped quantized noise to wiggle at high frequencies and ride over the input, the U must be smaller by some amount. So then, if this is the quantizer range, then this might be the stable input range for U, and the ratio of stable input range by quantizer range is called maximum stable amplitude, or MSA. And then the question is, what happens to MSA when we move to higher and higher order modulators, basically higher order NTFs? So simply it will decrease because the gain of the outband noise, so in-band noise is being shaped to outband, but the gain of the outband noise will increase as the order of the NTF will increase, and thus the variance of the noise riding over the input, which is seen by the quantizer, increases, and which increases the probability of saturation of the quantizer, and in the end it makes the loop unstable. So this is how this is all about the stability of um, delta sigma modulator. And then obviously we have to make the trade-offs dependent upon MSA and other factors. So that's all for this video from my side, and thank you so much. And if you have doubts, please let me know.